gentlemen, it's time for another exceptional stretch brought upon one of the rousing topics in the field of technology, which is the fifth generation of technology, or you call it 5G technology. I welcome you all to this seminal event organized by IEEE TechVerse Sri Lanka. I'm Vidara, a member of IEEE TechVerse Sri Lanka, and I will be your moderator for tonight. To start off today's proceedings, let me brief you about IEEE. IEEE is the Institute of Electrical and Electronic Engineers, which is the world's largest
Recording in
technical and
progress.
professional organization dedicated to advancing technology for the benefits of humanity. So we are IEEE TechVerse Sri Lanka, and we want to make sure that you know all the cool tech stuffs out there. So every month you can catch us either physically or virtually like this for awesome tech talks. And if you're into reading, we've got you. Check out our creative article platform, which is TechScribe. And we have another interesting thing that's our very own podcast series. So where we dive deep into tech topics. And if you're into creating content, we've got content video competition for you all. So stick around because this year we are kicking off the tech journey as never before. So let me stop talking. Now it's the time that y'all have been eagerly waiting for. I would like to welcome our honored guest speaker for this evening, Mr. Anuradha Udunuwara, seasoned telecom and technology expert with over 2 decades of industry experience encompassing strategy, architecture, engineering, design, planning, implementation, and maintenance of CSP, DSP networks. His expertise extends from legacy to solution designing. He is a senior engineer at SLT Mobitel, entrusted with consulting, advising, architecting, and planning technical solutions for enterprise customers, which he is also actively involved in shaping SLT Mobitel's digital transformation journey, including the transformative world of 5G. He is also a guest lecturer at University of Peradeniya, where he imparts knowledge to final year electrical and electronic undergraduates. We are privileged to have such an accomplished academics joining us here today. So, ladies and gentlemen, please warmly welcome Mr. Anuradha Udunuwara. Over to you, sir.
Okay, thank you very much for the introduction. Let me share my slides. I hope you can see my slides.
Yes, sir.
Okay. All right. So let's get started. And as mentioned, like we are going to talk about 5G today. And I have titled my session as what, how, and when. And there should be a bit of why as well. So although I will not go one by one, the intention of today's session is actually to touch on these 4 areas, like what is 5G, how it is done or how it works, and probably why we need 5G, and also a question that we have, especially in Sri Lanka and markets like Sri Lanka, is when to go with 5G, given that we already have like the previous generations of mobile technologies running, naming 2G, 3G, 4G, etc. When should one or when should a service provider or an operator invest on 5G? So one of the issues that I see based on my little experience in this domain for the last 20 years is that when there's a new technology or a new buzzword or a new term comes in, people tend to read about it, talk about it, and sometimes debate about it. But most of the time, I see it's only at the surface level. So different things at the surface level. So it's very important, whether it is 5G or something else, that we go at least a couple of levels below and try to understand the core fundamentals behind that particular technology or the term. So I thought of starting the session that way, so that one could understand the rationale behind, or the logic behind of all these technology innovations, or maybe all these generations. Now, before getting into 5G, let's look at what are we trying to do here. So what is the problem we are going to solve? At very high level, we have a wireless device, right? Need not be a mobile device, need not be a mobile phone, any wireless device, meaning that it's connected to the rest of the world wirelessly. So we have a wireless device. And then we have a host of ICT services. It need not be the ICT services that you and me consume on our mobile devices in daily basis, like the apps, accessing internet, making a voice call, texting someone. Those are basic ICT services, but there could be other ICT services as well. Maybe a data connection used by a specific wireless device in a factory to do a specific task without human intervention. Right? So it could be voice, video, data, controlling, internet, multiple ICT services. So when you say ICT, I broadly categorize, or rather I broadly put all of those ICT services that you can imagine to this bundle of ICT services. Now, this wireless device on the left-hand side of mine is actually trying to consume the ICT services. So on the other hand, the ICT services, the provider of the ICT services is trying to push or deliver those ICT services to the wireless device. So that is basically what we are trying to do. And doing so, we understand that there are service providers, telecommunication service providers or ICT service providers who provide services like SLT Mobitel. And they are also operators, meaning that they operate and maintain networks. So in some countries, we find operators who just do the operation of networks, and on top of that network, different service providers provide their services. But in this country, we don't have that type of environment. We have service providers, operators, both doing the operation of the network and providing their own services on top of that network. So we have service provider transport network, which means providing the transport across the country, sometimes between countries, between continents, etc. So that is the service provider's transport network. Because all these services today are IP-based, packet-based, so you need to transport them, let's say from Colombo to Kandy, from Kandy to Peradeniya, etc. And then you have in the same network, we specifically identify another part of the network, which is called the service provider's access network. The term access means that it gives access to the end device or the person at the end of the network who's actually trying to use these services or consume these services. So service providers access network could be like wireline network, like copper or fiber, or it could be wireless network. So in today's discussion, our focus is on wireless. And then whether the device or whether the person who's carrying the device consuming or not consuming that particular service depends, among many things, depends mainly on the connectivity that wireless device has with the access network or the closest point of presence of the service provider's network. So basically, we identify that closest point of presence in a wireless network as the conventional term called the BTS, or the base station, or the antenna, or the tower, or whatever the name, right? So if you have a tower in the vicinity, and if you can see a tower, that means, of course, if you are getting the wireless signal to your device, that means you can get connected to this access network, and then your traffic can be transported to the edge of the service, which is your ICT services, and vice versa. Your ICT services can be transported across the transport network, across the access network, and wirelessly deliver to your wireless device. Now, the question is, I have put a question mark, is on this access part, and that is mainly where the 5G discussion is actually turning around. Now, in this case of wireless, your access network becomes a special type of access network, and we call that a radio access network. Radio means not the radio that we listen to, but the radio signals, or the radio frequency signals, one part of the electromagnetic spectrum that we have for all types of communication, whether it is radio, television, mobile communication, wireless communication, optical fiber communication, or the communication that we have on electrical conductors like copper. All that falls within this total electromagnetic spectrum, and we use the radio part of it for radio access networks. So that is what we are trying to do here. And then in terms of the last mile access, that is the access between your device, it could be your laptop, it could be a router, switch, a wireless device, any other device, or maybe in a very high level view, you can assume that is your house, or that is your business, or your shop, or your enterprise, institution, organization, whatever, or maybe yourself, a person, a human being. So that is the one that is on the left hand side. And the last mile connectivity could be, as I said, could be copper wires, coaxial or twisted pair like copper wires, optical fiber. Predominantly these days we use optical fiber for last mile connectivity, or it could be wireless. Now in all these three categories, we see an electromagnetic signal is being sent from A to B and B to A. In the case of copper, we identify that electromagnetic signal or the wave as an electrical signal, which means it has the association of things like voltages, currents, etc. And that is how you actually sort of feel it, that electromagnetic wave. And on optical fiber, again, it is an electromagnetic wave, but in this case, we use light as a signal. So you use the light signal to transport your information. So in that case, you feel, you understand the electromagnetic circuit signal as light. In the case of wireless, means no wires, we use the air to radiate an electromagnetic wave. So in that case, our media is actually the space or the air between the two locations. Now, if you look at the electromagnetic spectrum, as I said, it spans theoretically from 0 hertz or 0 meters. If you take the wavelength format, because you can explain an electromagnetic wave, which is a sinusoidal wave, in two different parameters. One is the frequency, the other one is the wavelength. Both are interrelated. So it goes to infinity, but for all our practical discussions, it looks something like this. So visible lights falls within so many micrometers to so many nanometers. usually when you talk about light, we don't talk about the frequency. We usually talk about in terms of the wavelength, nanometers. For example, in our optical fiber backbone network, we use wavelengths like 1550 nanometers, 1310 nanometers, 1490 nanometer light signals. So when you translate those nanometers into frequency, you find that those frequencies are in the range of 150 terahertz to 250 terahertz. So high frequency signals with small wavelengths. So that is used in optical fiber communication, and the format of that electromagnetic wave is light, right? And then the lower end of your electromagnetic spectrum, you have, for example, 0 megahertz to 20 megahertz is used in your copper networks like ADSL networks, the broadband copper networks, small spectrums. And in between, you have something like 600 megahertz up to 300 gigahertz. That is actually the radio spectrum that is being used for various wireless communication requirements. And if you expand the radio spectrum further, you will identify, while there are multiple spectrum segments like hertz, kilohertz, megahertz, gigahertz, terahertz, the radio spectrum is basically in between like 3 kilohertz to something like 300 gigahertz. And even in that, the mobile communication, the wireless communication uses the frequencies from 600 megahertz to 300 gigahertz. And if you really want to visualize an electromagnetic wave, it would be something like this, shown in this graphic. You have an electronic component to that waveform, and also a magnetic component to that waveform, going in the same direction, but in two different planes perpendicular to each other. So you can derive all the equations that you need to actually analyze these type of signals. And these are called electromagnetic waves. So whether it is an electrical signal, whether it is an radio frequency waveform, or whether it is light in your optical fiber, you find it is an electromagnetic wave. Now, what's the problem with a channel that you use to communicate from one location to the other and sending an electromagnetic wave from one location to the other and vice versa? You have certain laws of physics because you go through a media. You start with certain power in your electromagnetic signal, but over the distance, you lose power of that signal. And that is why you cannot send a signal from one location to, let's say, from here to Japan without regenerating that signal. Because over distance, it loses its power. And the characteristic of the media will decide how the power is actually lost over the distance. And for wireless communication, we have something called free space path loss, which means an equation like this. Basically, your loss is proportional to your distance squared and the frequency squared. So what does that mean? If you really compare your signal loss, because when I want to, let's say I'm the base station and you are the wireless device, I want to send you something and I use an electromagnetic wave and I do modulation and all of that, and sort of put all the information that I want to communicate from my location to your location into that electromagnetic wave and send it across the air, expecting that it will reach you, right? But for it to reach you and to travel from this location to where your wireless device is located, it needs to have certain power. Without power, like for example, if it is a vehicle, if it does not have power or the gas, it doesn't move, right? So you need certain amount of power. So you insert power also to that signal, and then let it transmit across the media. So if you really look at how optical fiber works, over distance, the loss is sort of like for you to see a significant loss of the original power, you have to go a distance something like, let's say, 20 kilometers or 10 kilometers. Then only you will notice that you have lost power. If it is copper, the power loses very fast. Both are linear, but in copper, it like 5 to 6 kilometers, you lose the power. And if you take wireless, because of the reason that your loss is proportionate to distance squared and the frequency squared, I have not considered frequency here. Just considering the distance, you have an exponential decay of signal loss over distance. But it's not just the distance, it has a frequency component to that as well. So it depends what frequency you use and how long you want to reach with your wireless signal. So in designing wireless network communication systems, you have multiple constraints, multiple parameters that you need to consider. For example, the frequency, the capacity, the distance, the penetration, and there are a few others. If you just consider the frequency, right? If you increase the frequency, you get access to larger spectrum. For example, if you take 0 to 1000 megahertz, the total spectrum you have is 1000 megahertz. But if you consider 1 megahertz, so 1 gigahertz to 300 gigahertz, the total spectrum that you have access to is 300 gigahertz or 300,000 megahertz. And if you have more spectrum, you can get more capacity or the bandwidth. So that is actually, there's a direct relationship, one-to-one relationship between the spectrum in hertz that you have access to and the amount of capacity bandwidth that you can get out of your channel, which is measured in bits per second. So these days, for example, SLT Mobitel delivers fiber to the home connections with 1 gigabits per second. And how do you achieve that is based on that terahertz spectrum that we have in optical fiber communication. So same applies whether you are using wireless channel or a copper channel or whatever. So that is called the Shannon's capacity theorem. So one would prefer to have larger frequencies. For example, like if you go to the range of 30 gigahertz range, you have so many hundreds of megahertz spectrum. But if you're operating in 800, 900 megahertz region, like your GSM 2G networks, you have access to very small amount of spectrum. And the other constraint is, as we discussed, when the frequency increases, your signal power loses, right? When the signal power loses, the distance or the coverage that you can achieve also goes down. So that is called the free space path loss. And on the other side, higher frequencies, like the frequencies in the range of over 6 gigahertz, 6 gigahertz to, let's say, 30 gigahertz, which is also referred to as millimeter wave, has certain difficulties in penetrating buildings, the structures, etc. So the whole wireless design sort of discussion has all these parameters which you need to actually optimize. You want higher capacities, you want to go for higher spectrum, which means higher frequencies. When you go to higher frequencies, you have other issues. So you have to balance out all these things. And pictorially, you can visualize it something like this. For example, millimeter wave, which operates from up to 30 gigahertz, including 24 gigahertz. So This is called millimeter wave. It has higher capacity, but shorter distance. But if you go to 600 megahertz to 2 gigahertz, something like your GSM 3G network, it has larger coverage, but lower capacity. So the engineers or the people who worked in this domain started looking at how to improve this. You know the constraints, the parameters, and then how to improve it. And they came out with all these generations, right? From 1G to 5G and coming 6G. Now, 1G up to 3G is basically called mobile, because the 1G phone, which is an analog phone, and the 2G phone and the 3G phones were all mobile phones. So it is okay to call 1G, 2G, 3G as mobile generations, right? But after 4G, 4G and 5G and also 6G, it's sort of incorrect to call them just as mobile generations. The more proper term is to call them as wireless generations, because 4G can be mobile or fixed. We have 4G fixed, 4G mobile. Same for 5G, same for 6G, right? So what has happened over the years is that just starting with analog voice, we moved to digital voice with SMS, and then voice SMS plus mobile broadband, right? And then with 4G, we enhance the experience of mobile broadband, basically increase the capacity and also reduce the latency or the delay. And going forward with 5G, we further enhance what we had with 4G, plus adding the capability of carrying different traffic types. And that is why a lot of people say that 5G is not just for people to make voice calls and to browse internet, but it is more about connecting not just places and people, but connecting things. Internet of Things, industrial IoT, consumer IoT, smart factories, Industry 4.0, all of these things, connecting devices. So when you connect devices, you need different capabilities depending on the type of device that you're going to connect. So if you look at the global traffic growth, for example, this is although the year-on-year growth rate is declining from starting from the COVID, it looks it's further declining, but the overall aggregated traffic is now reaching over 120 exabytes per month, right? Total, no, yes, 120 exabytes per month. So there is a huge amount of data being transported across mobile networks, which includes, by the way, both fixed and mobile. Now, when it comes to all these generations, right, from generation 1 up to 6, there should be someone or different organization who's actually regulating this in terms of standards and standardization. In telecommunication and also other parts of engineering, standards are important because then only you can interwork, intercommunicate, interoperate with other entities and other devices, other systems, subsystems. You need standards, and standardization is actually everybody respecting that standards and embracing that standard in that particular community. So 3GPP, which is Third Generation Partnership Project, is one big umbrella standardization organization who's actually working with all these other standardization bodies, like some are country specific, some are region specific, but they're working together to come out with a globally acceptable set of standards for these old generations of wireless communication. And here I'm trying to sort of combine the history of wireless and mobile communication from the early 80s up to 2040, for example, starting from the traditional communication technologies like 1G, 2G, 3G. By the way, these dates do not exactly fall like 80 to 90s 1G, 91 to 2000 is 2G. There are certain different gaps, but generally it is 80 to 90, 91 to 2000, 2001 to 2010. Every 10 years you get a new mobile generation. So we are now living in the 5G generation. For us to have 6G in 2031, you need to start working on 6G now. That is why, for example, University of Oulu in Finland, they are working on 6G, and some other countries also work on 6G. Commercially, 6G will be available based on these numbers, these timelines by 2031. For us to have 6G in 2031, we should start researching it these days. Since we started researching on 5G and inventing 5G, working on 5G in like early 2010, 11, we have 5G today. So it has a considerable time for us to do research and development and then to commercialize it. So if you look at the multiple differences, you have like 3G comes as releases. For example, if you take phase 1 up to release 98 is about 2G, and then release 99 up to release 7 is 3G. Likewise, then you have 5G is actually release 14 up to release 20, and then from 21 it starts 60. So that list goes on. And ITU, International Telecommunications Union, also started their own way of defining these standards as IMT standards. So relevant IMT standards for 5G is IMT 2020. The previous generations up to 3G, more traditional way of architecting the radio access network. But from 4G onwards, the network is end-to-end IP. All the traffic types that we discussed are based on IP and packet communication. So it's end-to-end IP and the network is virtualized. And in the world of 5G, again, your traffic is end-to-end IP, whether it is voice, video, data, or any other traffic, starting from your wireless device up to the service edge. Everything is IP-based, and it is also cloud and cloud native based. That's the difference between 4G and 5G in terms of the network architecture. And these terms mostly confusing in general discussions like what is LTE and what is 4G. 4G is the generation, the generic name given to that particular generation. LTE is the wireless technology between your wireless device and the base station. Or in 4G, it is called the E node B. Similarly, we have a wireless technology called New Radio, or NR, between the 5G wireless device and the 5G base station, or which is called G node B, right? So LTE is not 4G, but it is also 4G, but 4G is the generation. LTE is the wireless technology that we use in the air interface. Although the earliest, the first mobile generation, the 1G was analog based, 2G onwards, it is all digital based. And this basically gives you a very high level understanding of how these generations evolved over the years. So I think it's very important that you have that background or the history for you to understand what is 5G, because 5G did not happen like magic, right? 5G has the 5th generation. When you talk about the 5th generation, it means that it had like 4 other generations before that, and it's a continuation of the continuous innovation, continuous research and development, the improvements, bringing in new capabilities, etc. So that is something that is continuing over the years. So 5G basically delivers 3 things other than the things that the previous generation used to deliver. One is enhanced mobile broadband in higher capacities of mobile broadband. Although it's mentioned in IMT 2020 as mobile broadband, it is enhanced wireless broadband because it includes mobile and fixed both. And then you have ultra reliable low latency communication, which is not a concern up to 4G. 4G networks did not concern about the latency between the communication. For example, you are playing a multi-party video game over the 5G network, latency matters, and 5G specifically consider latency as one of the design parameters, and it is one of the capabilities that it delivers to end services, ultra reliable low latency communication. The third capability it is supposed to deliver is massive machine type communication. So this is the area we talk about IoT, the billions of devices or the things that 5G is going to connect between devices and people, devices and places, etc. So this is basically what 5G is expected to deliver. And if you really look at the history from 2017 up to 2022 or 23, you find that in 22 we had like 8.3 billion subscribers. By end of by 23 we have 1.5 billion 5G subscriptions. So when you say subscriptions, it doesn't mean that 1.5 billion people connected on 5G, because 5G is not just about people or places, it's also about things. So that is why the word subscriptions, the subscription could be a personal mobile phone, it could be any wireless device, it could be any Internet of Things device. So 5G, the orange area is actually growing. It is expected to grow like 9.1 billion altogether, but in that 9.1 billion, roughly 40% of that is going to be 5G by 2028. Any questions? Somebody wanted to ask something? No? Okay. So that access network becomes radio access network, and in typical wireless mobile communication, you have your device here, and then you have the antennas, radio units, and then you have your communication to another device called the BBU, baseband unit, and then the base station controller. This is how the architecture for in any general mobile communication network. So you have digital to analog communication, because radio frequency, as we discussed, it's about frequency. It's a sinusoidal wave, so it is analog. But rest of the discussion is about digital, IP, and packet. So you need to convert from digital to analog and from analog to digital. So that side is analog. Your wireless side is analog. Your transport side is digital, and then you have different ways you transport. You transport initially as baseband, and then you multiplex it and convert it to broadband. Different conversions, modulations, and multiple other things involved in between. And you might have also heard these terms called the front haul, back haul, mid haul. These are actually terms used to describe how these different segments of the network is connected to the other segments. And another two terms coming with RAN, radio access network, is virtual RAN and open RAN. Virtual RAN is nothing but you try to virtualize all these middle components like the BBU, BSC, all these control components virtualize, meaning that that capability can be run on a standard x86 server, standard server or a virtualized server. So that is called a virtual RAN, right? And then you have something called Open RAN, which is nothing but your interfaces are open. You use open standards, right? So if one component coming from Huawei, another component coming from, let's say, Ericsson in my wireless network, if both those two components support open standards, I have no issues in interconnecting them and running my network. So Open RAN, although need not be virtual, it is usually virtual. Virtual RAN is nothing but virtualizing all these middle components. And in 5G, we use virtualization to its maximum. Other than the radio that we have in this G node B, everything else is actually IP based, packet based, it is digital, and it is also virtualized, and also it uses cloud and cloud native technologies. So it's just a matter of, you can imagine it as multiple computers interconnected in the transport network. Right? You can see it has hardware, which is the radio unit. It runs software and APIs, but in between, these are all servers, standard computer servers, but hardened to telco environments. And in terms of architecture, it is also moving from a hierarchical to a more flatter network architecture, more simple network architecture, centralizing all the control here and just have the RAN. And going forward, you can see when you move from 4G to 5G, you are again making that centralized architecture to a more not decentralized, but it is a more distributed cloud architecture. That is why in this diagram shows clouds. And these clouds carry all these computing devices, the server, storage, networking, etc. So you have your wireless device, it is connected to your G node B, which is your base station, over new radio, which is your wireless technology. And after that, it is actually, your traffic goes from this server to this server, like that. So it's a distributed cloud architecture that we have in 5G. And if you try to compare the previous generations, you will see that we are moving from traditional to virtualized to cloud native architecture when you go from 3G to 4G to 5G non-standalone to 5G standalone. And that is why 5G is different from all the previous generations of mobile technologies. Like you can see, those who are doing computer engineering or computer science, we use the cloud native technologies like Kubernetes, Helm charts, Prometheus, Docker containers, other containers, and multiple other cloud native technologies to realize 5G. So 5G is not just the radio part, right? So 5G is end to end, and there are multiple pieces that you really need of different nature compared to the previous generations. So where is 5G? If you really look at, these are multiple technologies like wireless technology, AMPS, GSM, UMTS, LTE, and now new radio. So that is your wireless technology between your wireless device and your base station, which is G node B. And then you have to control all of that. You have a mobile core. For simplicity's sake, I have just drawn it as one single box, which is your 5G core or 5GC. In the 4G world, it is called the EPC, Evolved Packet Core. And that is, those are the components that actually makes this connectivity happen. But actually, this mobile core is actually distributed. your RAN is distributed, some pieces of the core is also distributed across this network, because it can be distributed because these are virtual capabilities and they are based on cloud and cloud native technologies. Now, if you quickly look at the current status of 5G, this is how it looks like. So we have a world of 7.8 billion people, 11.7 billion cellular connections, 255 5G networks, over 1,500 5G devices, and around 2 billion 5G subscribers. This is, I think, more updated than the previous statistics I showed you, including IoT. So when you say 5G subscribers, always remember that it doesn't mean that 2 billion people connected. It's 2 billion subscribers, which includes devices plus people. And in Sri Lanka, we were the first to launch 3G in South Asia. We launched 4G in 2013, currently trialing 5G in 3.5 gigahertz, because the Sri Lankan regulator has not yet auctioned the 5G spectrum. Once the spectrum is released, we can implement 5G as well. And these are some global statistics, which is basically the same stats that I showed earlier. But you can see, for example, there are more than 2,000 5G devices announced. So these markets are growing, like although 5G devices are quite expensive in current Sri Lankan context, you have over 2,000 5G devices available in the global market for you to choose. And the global mobile data traffic is actually increasing, and you need a technology which can actually cater to the growing demand of all this mobile data traffic. And that is why you need, that is, by the way, not why you need 5G. To cater to growing data demands, you need higher capacities. For higher capacities, you need larger spectrum. When you have larger spectrum, you can get high capacities. Larger spectrum is available in higher frequencies, and then higher frequencies can be used by 5G to deliver the so-called capabilities. And this is how the mobile subscriptions in different regions, for example, if you take Southeast Asia, you can see there's small 5G deployments, but it is expected across the world, it is expected that by 2028, for example, if you take North America, by 2028, 91% of the subscription is on 5G. But for us, for example, if you take Southeast Asia, it will be like 34% even in 2028. So our growth will be slow. And as I said, it's not just mobile, it has fixed wireless access component to it as well. So it is also growing, right? 5G is going to deliver, basically 5G can replace a point-to-point wireless wired connection, or it can replace fiber, it can replace copper with proper design. And the IoT connectivities, all these subscribers, which includes people and things, is also shown here, that it is also expected to grow, that 5G is going to connect more devices, of course, more people, more devices, more places, etc. And then the population coverage, we have two things. One is the geographical coverage, the population coverage. We are more concerned about the population coverage. There's no point covering, for example, although it's good to have the coverage in a thick jungle, because sometimes you go inside jungles, but usually the investment pattern is to cover the most populous areas. So the population coverage of 5G today is like something like 35% on average around the world. But if you take specific markets, like for example, in China, it is 90%. In Asia, it is 12 to 13%. So Asian markets need to grow, excluding China. And why 5G is important today? If you really look at from 2020, when people invested on 5G, right? When the 5G subscription increases, the orange line, your revenue also started increasing, right? So that is why the operators are actually investing on 5G because it has a business case for them to increase their revenues and also increase their profits. Now, what are the issues we have? Specifically in Sri Lankan context, we need spectrum. The regulator has to release the spectrum. And the country demographics, if you look at like 5G, it is understood that 5G will take at least 15 years to get 80% population coverage in developing countries like ours. Right? So this is if you think that as an operator that you can make it a profitable business by covering 80% of the population, it will take 15 years. And the profitability and return on investment, if you take like, it will cost for the spectrum and the other capabilities, the infrastructure, the towers and all of that, something like 200 to 250 million US dollars. And we are still struggling to come out with the economic condition we have, the inflation, the rupee devaluation, forex changes, and 25%, over 25% of the Sri Lankan are under the poverty line. And our average revenue per user is less than 2.5 US dollars, whereas in developed countries, it is over 20 US dollars. So if you consider all these constraints, the economic constraints, it probably is not the right time for us to go for 5G or invest on 5G. I would say it can wait till something like 2025. And in terms of challenges, power is a huge challenge for us. You know, the power tariffs from the utility companies are very high these days. So all these locations need to be powered. And you can see when you run multiple generations of mobile technologies on the same tower, for example, 2G to 3G, 2G to 4G. And for example, if you are to run 2G, 3G, 4G, and 5G on the same tower, you're talking about huge amount of power consumption. And that is why it is very important for us to shut down 2G, 3G networks. 3G networks are almost shut down in Sri Lanka, but 2G gives the highest population coverage. So you cannot shut it down unless you have equivalent coverage with 4G and 5G. So it's very important that you keep at least 2 technologies going in parallel, not 4 technologies. Because then you are actually challenged with the power bills. In terms of alternate solutions, you can have public-private partnerships, co-invest the government and the private companies together, form alliances, have discussions, then the regulator supporting, for example, utilizing electricity poles as towers, etc. And also look at the carbon footprint and the energy consumption, and look at, for example, the picture you see here is a renewable site, not in Sri Lanka, wireless site actually running out of wind power. We have towers running out of solar power, you can have wind power. So these are some of the solutions that the world has tried in terms of finding especially solutions to the power problem. So my last slide is that 5G is not the destination. So we will not stop at 5G. I'm not sure whether we will stop at 6G, but the chances are that 5G will become 5G advanced. What we do then is actually to make enhanced mobile broadbands more advanced, like bringing things like artificial intelligence and machine learning. Then ultra reliable low latency communication will work with time sensitive networking, and same for machine type communication. So that is 5G advanced. And then we will go to 6G, keeping the so-called the triangle, which is to enhance mobile broadband, ultra reliable low latency communication, and massive machine type communication. So that is the kind of foundation 5G to 5G Advanced is an enhancement. 5G Advanced to 6G is not another generation actually. It's an expansion of 5G. So that is why you still have the triangle and the core capabilities, plus you bring in basically capabilities plus different use cases that you can achieve with 6G. So that's it I have in terms of what I plan for today's discussion. So I hope we have a Q&A session. We can move to that.
Yeah, thank you, sir. Your session have made a memorable note towards me and our virtual guests. So IEEE TechVerse would love to give our gratitude for you for sharing your knowledge with us. So before we come to an end, I'd like to offer a platform for question and answer session. So if you have any question regarding today's session, you may ask now. And to ensure that we have enough time to answer many questions as possible, make sure you make your questions to the point. Yeah, you may ask now if you have.
So I have a couple of questions. No. Okay. No questions in the chat. So
yeah, you can unmute your mic and speak if you have, or else you can drop it to our chat box as well. All right, I got a question from shared platform. So yeah, one have asked, how will 5G impact the Internet of Things?
Or rather, it's not, I think it's the other way around. So not 5G impacts IoT, but IoT impacts 5G, because the whole purpose of technology like 5G or a generation like 5G is actually to support IoT, because the previous generations by design was to provide these mobile broadband voice kind of stuff, mainly looking at a device actually carried by a person. Whereas the 5G design, by design, it is actually looking at different data types. So these different data types include different data types generated by all these IoT devices. So IoT needs 5G for connectivity, and together, I think we have a lot of use cases like industrial automation, factory automation, autonomous vehicles, unmanned sites like the mining sites, which can be connected. So when you say unmanned, there are no people. So it's devices, the forklifts, the excavators, robots, etc., all communicating using 5G technology. If it is not 5G, you have to use a technology like, for example, Bluetooth or Wi-Fi, which is by design is not designed for that purpose. And that is why when people design 5G, they came out with these ideas of massive machine type communication. So the whole capability of massive machine type communication is just to address the IoT requirements. I hope that's clear.
Yeah, I hope she got the answer. And we have another question. Yeah. Sir, I used to work as a customer service agent at Dialog. We had so many customers complaining about 2G and 3G not being available, especially in rural areas. Won't 5G affect these people even more? Yeah, and mention, sorry, not 2G, 3G not being available.
Yes, 3G is actually not available. Like it is being sort of discontinued by most of the operators, because there's no point an operator running 2G, 3G, 4G, 5G, multiple generations of mobile technologies. That involves CapEx, but CapEx is already now invested, but it involves OpEx as well, operational expenditure. You have to keep multiple skill sets, multiple sets of spares, multiple operational costs, etc. And 3G, if you take the spectrum, it's all about the spectrum, right? So if you have a spectrum, which is a finite resource, you split the spectrum into 4, 2G, 3G, 4G, and 5G, and use part of the spectrum in these generations. Now, the idea is that you get rid of the older generations and recover the spectrum and reform that spectrum in other generations. So the meaning of shutting down 3G is actually to recover that spectrum being used today by 3G and to reuse that it probably with 4G and 5G to have higher capacities, because when you have large access to the spectrum, you get higher capacities. So that is the idea. Now, the specific question with regard to the customers complaining about the unavailability of 3G is one reason is because the 3G networks are being shut down by the operators because they are reforming the spectrum in 4G, and probably they are not timely expanding their 4G networks to the areas where they do not have 4G and 3G coverage. So it's big. It's not really a technology thing. It's really a business thing that the operators need to work on to expand their footprint in terms of 4G and 5G going forward. So I see another question in the chat. I heard that 5G tech cause severe environmental complications. If so, what are the methods undertook to reduce these kind of implications? So it's not just 5G. That is why I started with the basic introduction of wireless communication. Wireless communication starts with a wireless signal, which is an electromagnetic wave modulated with the information that you want to transmit from one location to the other with a certain amount of power, right? So the usual regulation is if that power is less than 2 watts, there's no problem even if that wireless signal comes and hit your body. We are human beings are made out of, like, I think close to 90% or something like that of our structure is water. Water absorbs RF signals, same for vegetation and other animals, etc. So we usually absorb all these wireless signals. So that is the physics of the environment. But if that absorbs wireless signal is less than of 2 watts of power, then you have a problem with your internal human structure. So that is why all the mobile devices brought into Sri Lanka is heavily regulated by the regulator and certified to make sure that they are within those limits. But any specific health risk or environmental risk, all these things are not scientifically proved based on facts by anybody up to now. So I don't think there are concerns, but there are concerns because you're going to have more base stations than what you used to have with previous generations. For example, if you had 1,000 base stations with 4G, you could have like 10,000 or 20,000 base stations, or even more than that with 5G. But still, then you are distributing your workload, and you can work with smaller capacities in smaller cells. So it is not scientifically proven as yet the specific challenges or the threats that we have to the environment or to the humans. There's another question from Deloge. 5G tower is being set up in Sri Lanka, and what is the current situation? Yes, SLT Mobitel and also Dialog. We are running 5G test networks on 3.5 gigahertz in designated areas. If you visit the respective websites of these two operators, you can find what are the locations. For example, SLT Mobitel has site here in Kandy, in Colombo, and multiple other places. So if you have a 5G device, you can go and experience 5G. So you don't need a new SIM card. you can activate 5G with using your 4G SIM card, or if you have an eSIM, that is also possible. So you can get connected and use that. When you say a tower, by the way, tower is the metal structure. On a tower, you can have multiple operators or multiple generations of wireless and mobile technologies. So we are still waiting for the regulator to actually release the actual spectrum, which we don't know, which could be something like 2.3 up to 3.6. We hope. So once the spectrum is released, we can go officially, commercially launch 5G in Sri Lanka.
Yeah, and we got another question. What are the security concerns associated with 5G networks, and how are they being addressed?
Now, the security concern, if you carefully followed what I discussed from the very beginning, we are moving from an analog world to a digital world. We are moving from a more conventional sort of rigid static network architecture to more dynamic, more distributed, more like democratic, end-to-end IP and cloud architecture. So when you move to a system architecture which is based on IP, Internet Protocol communication, and cloud native, we are actually expanding our threat landscape. If it is not IP based, of course, they are more rigid, but then there are certain ways that you can hack even that type of a network as well. But when you're talking about end-to-end IP, cloud and cloud native type of network, you're actually expanding your threat landscape. So there are various ways and means to address that, and it's not easy. So security cannot be an afterthought when you design a 5G network, because you need to really understand, and that is the whole purpose of my discussion also today, to give you the basic fundamental knowledge that you need to understand in any wireless network technology, not necessarily 5G, so that actually you can understand 5G better. Right? You can find enough information about 5G in other places as well. So you need to address security in all these places that I mentioned, because now you are exposing your network with IP and cloud native technologies. It's not easy, but it's something that you have to do, you must do as an operator or as a service provider.
Yeah, and somebody asked, can we get the copies of the slides?
Yes, I will share it with you. If you just remind me over an email, I will reply to you with the slides. No issues.
Okay. So any questions? So I hope there's no more questions, and I hope you may have acknowledged and made everything clear. Now it's time to present our graceful appreciation to Mr. Anuradha Udunuwara for being here today and sharing your knowledge with us. So please accept this token of appreciation for your contribution toward making this event a success. Once again, thank you. Yeah,
thank you very much.
Thank you for sharing your valuable insights and making a significant impact on all of us. It was an absolute pleasure to have you with us today, and we sincerely hope to have an opportunity to hear you speak again in our future events as well.
Okay, I'll try to help you in whatever the possible ways that I can.
Yeah, thank you, sir. So now it's time to make this memory an unforgettable one. So I would like to ask everyone here today to turn on your camera so that we could take our group photograph. And meanwhile, a feedback form will be shared among you through the chat box. Please spare a minute to fill that as well. So
Somebody
if you can,
says,
please turn on your cameras. They don't have permission.
yeah,
Now you can.
Okay.
Thank you. We'll wait one more minute until others will turn on their cameras. So right, let's take the photograph. I'll give a count. So 3, 2, 1. All right, thank you so much. And thank you for joining us today. We truly appreciate your presence at our event. As we have come to an end of today's proceeding, your moderator will be signing off. To stay on update on our future events, make sure you keep in touch on us in our social media. We look forward to keep in touch with you and see you again in our future event. Until then, good night.
Good night. Thank you.
Thank you.
Recording stopped.